All right, ladies and gents, today we are going to go over kind of the big picture of where we are so far, and then we're going to talk about our last two electron configurations that we're going to do. One's the shorthand and the other one is Lewis dot. Both very simple if you understand the electron configurations and the orbital filling notations. So at this point, if you're still struggling with those, you should be getting in touch with me to get additional help. Looking on YouTube, looking for Tyler DeWitt, Marissa Maribel, Organic Chem Tutor. Those are three folks that do a lot of tutorials on this stuff. If you're not proficient at that at this moment, you should probably pause and go back. Make sure that you understand electron configurations, filling order, and orbital filling diagrams. What I want to do real quick is kind of do a big picture review of what we talked about so far. So on our periodic table, what we've uncovered thus far is that there are 7 rows on the periodic table. Okay, each of whatever row an element is in, that's how many energy levels or layers it would have in its simple atomic model. Okay, the main group elements, the number in the ones place is the number of valent electrons, which is going to come into play today. The main group elements would be groups 1, 2, and 13 through 18. 1, 2, and 13 through 18. So that would be your S and P block. The S and P block consist or make up the main group elements. The number of electrons each energy level can hold is 2 times the energy level squared. We talked about that the first day we started breaking into this. We should remember that the F block, which are the lanthanides, and the actinides fit in between groups 2 and 3, starting in row 6. They are 2 behind the row number, so in row 6 we run across the 4F, and row 7 we run across the 5F. Also remember that the D block is 1 behind the row. So starting in row 4, we have the 3D. In row 5, we have the 4D. 6, we have the 5D. And in row 7, we have the 6D. When we're talking about how we make these electron configurations, there are 3 principles or rules that we need to follow. First and foremost is the off-ball principle. Sublevels fill lowest to highest energy. A lower energy sublevel must be full before a higher energy one can get electrons, which means if we go through the filling order, 1s through 7p, the 1s has to be full before the 2s can have an electron in it. The 2s has to be filled before the 2p gets electrons, and so forth. You have to fill the previous sublevel completely. The previous sublevel has to be full before you move on to the next sublevel. Hund's rule says that any sublevel with multiple orbitals, that would be the P's, the D's, and the F's, each orbital must have 1 electron before any can have a pair, which means when we have multiple orbitals, so if we would draw out a P orbital here, you would give each orbital a single up arrow. That would be correct. You would not want to do up, down, up. Each orbital within a sublevel gets a single electron before any orbital gets a pair. And then Pauli exclusion principle tells us when we go to pair them up, they have to have opposite spin. That just means they need to be on opposite sides of the orbital. So we show an up arrow and a down arrow. Okay? That comes into play mainly with the orbital filling diagrams. Okay. Now, with that in mind, if we look at this very brief note card here on shorthand noble gas configuration. So sometimes it's called shorthand notation, other times it's referred to as noble gas configuration. You'll see why that is in a second. This is a condensed form of electron configuration that shows only the highest energy valence electrons beyond the last noble gas. Every noble gas has an S2P6 in it. So it has a full P6, okay? So when we go from a full electron configuration, so for chromium, which is right here, number 24, which remember, this is your 3D 1, 2, 3, 4, so it should end in 3d4. So we're going to go all the way through 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. We write out the configuration, and then there's two ways to do this. First way is write out your full configuration, and then at the end, go backwards until you find your first p6. So you want to go back until you find the first p6. That's the key thing. That's only noble gases have the p6. And then what we do is we take that whole chunk of our configuration out, and it gets replaced with the noble gas that is in that p6 location. So in the 3p6, so if we go to the third energy level, first energy level, second energy level, third energy level, 3p6 is argon. So we put argon in parentheses, and what that's saying is chromium is everything that argon is, 1s2, 2s2, 2p6, 3s2, 3p6, all that is argon. So chromium is argon and 4s2, 3d4. Okay? You do write the noble gas, the previous noble gas, in brackets, and then everything beyond that. So in the whatever the last row of the table is that you went through. If we look at silver, there's another example, but I want to show you a shorter way to do this. So if we look at silver, okay, what you want to do is you want to go back to the end of the previous row, which is krypton. We're going to put Kr in brackets, okay, put Kr in brackets, and then start on the row that silver is in. Silver is in the fifth row, so that means 5s2 is full, 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 5s2, 4d9 is what makes silver different than krypton. So silver is everything that krypton is, okay? It's everything krypton is, and 5s2, 4d9. Let's look at the next one. Let's look at iron. For iron, we go to the end of the third row, which is argon. We put argon in our brackets, okay? And then we pick up where argon was. So argon and 4s2, 3d6. 1, 2, 3, 4, 5, 6, and 3d6. So argon and 4s2, 3d6. That's what we call the shorthand configuration. Just to do a couple more examples from problems we've previously done. If we would go back and look at calcium, for instance. If we write out the electron configuration and then go backwards, look for the first p6. There it is. So that is what we're going to pull out. So what is 3p6? That's argon. So we would do argon in brackets, and then what's left is 4s2. Okay? Let's do another one. Let's do iron. Well, we already did iron, but let's do it again. Write out the configuration, go backwards until you hit a p6. Okay. Alright, so what is 3p6? That's argon. And 4s2, 3d6. Alright. Let's go to this one. How do we deal with oxygen? Well, oxygen doesn't have a p6, but it does have helium. Helium would be the s2. So we would go back. Previous noble gas is helium with 2s2, 2p4. Alright, let's look at osmium. Okay, osmium, really huge, long configuration. If we go backward until we hit the first p6, there's a 5p6. All of that can be summarized as 5p6 would be xenon. So we could do xe in brackets, 6s2, 4f14, 5d6. That's a heck of a lot easier to write that than write all that, correct? Let's do one more. Let's do fermium. So if we do fermium, we go backwards and we look for the first p6. Okay? 6p6, right here. 6p6. 6p is radon. So we're going to do in brackets Rn, 7s2, 5f12. Alright? So all you're doing, after you have the configuration done, you go backwards until you hit a P6, or if it's a small element, you're going back until you hit helium. And then you put the elements symbol, the previous noble gases symbol, in brackets, and then you write out the configuration on the last row. So it's radon, 7s2, 5f12. Okay? So we're going to try some practice with that in a moment. The next thing I want to go over with you is how do we take either a regular configuration or a shorthand notation and get what we call a Lewis dot notation from it. And this honestly is the most usable notation that we're going to have. The Lewis dot notation is an extreme shorthand method of electron configuration that shows only the electrons on the outermost energy level. That's called the valence electrons. Those are only on the highest number energy level, largest number out front. Everything else are core electrons. They're the ones that are not on the outermost energy level. So if we look at an electron configuration for germanium, we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. Look at all the numbers out front and find the highest numbers. 4 is our highest number. That's our valence shell. Take the subscripts that are associated with those sublevels and add them together. That will give you the number of valence electrons. Okay? You can do that from an electron configuration, or you can do that from an orbital filling. So if you have an orbital filling diagram, again, you're looking at all the numbers. Okay, there's a 4, and there's a 4. There's 2 electrons plus 2. That's 4 valence electrons. Now, what do we do once we figure out the number of valence electrons? Well, we take the element symbol, and we write it down. And then, in a very strategic manner, we place a dot to represent each valence electron around the symbol, and we do it in a clockwise manner. So we start and we put the first electron at the top, 12 o'clock, then 3 o'clock, then 6 o'clock, then 9 o'clock, and if you have a fifth one, you start to double them up. 6 will have 2 doubles, 7 will have 3 doubles, and 8 will have 4 pairs all the way around. So germanium has 4 valence electrons, so you would do dot at the 12, 3, 6, and 9 o'clock position. That shows us 4 valence electrons, and we need to make sure we show them as being unpaired or paired. Let's take a look at a couple of the examples we just went over. So what would we do with calcium here? Calcium, if we look at our numbers, our highest number is 4. There's 2 electrons. So you could just do dots or X's. That's how we would do it, 12 and 3. Let's take a look at something like oxygen. Okay, oxygen, highest energy level is 2. There's 6 total electrons in it. So we do 1, 2, 3, 4 at all the clock face positions, and then 5 and 6 valence electrons. Make sure that they are obviously paired or unpaired. That's a good one. What you don't want to do is this. That's no good. It doesn't do anything for us. Okay? We want to show them at the 12, 3, 6, and 9 o'clock positions. We want to make sure we know if they're unpaired or paired. That really helps us when we get to our bonding later on. Here's another trick, and you'll pick this up after you start looking at a lot of your electron configurations as we go. The number of electrons, valence electrons, for the main group elements is always the number in the ones place. So all the Lewis dot notations for everything in group 1 would look like this. It would just be an X with a single dot. All right? The element symbol, H with a single dot, Li with a single dot. Everything in group 2 would have 2 dots. All the transition metals have 2 valence. Everything in group 13 would have 3 dots. Everything in group 14 would have 4 dots. Everything in group 15 would have 5 dots. 16 would have 6 dots. 17 would have 7 dots. And 18 would have 4 pairs or 8 dots around it. We'll do some more practice with this. So you'll have an assignment to follow up, and we'll see on Friday or tomorrow, whatever day we end up getting through this, how we fare. And we'll go through the practice together, and it'd be a good idea to reference the scan of the periodic table that's available.